Thanking everybody for joining this online seminar series about games, decision, and network. For those of you who are new to this semester seminar, this is broadly about foundation and application of game theory, decision theory, and network theory, and we invite speakers at the intersection of economics, operational research, control, and computer science. And we have an amazing list of speakers upcoming. You can see more details about that in the website for this seminar series. And with that said, let me introduce today's speaker, who's going to be Professor Tomlin, who is a professor of electrical engineering and computer science at Berkeley, where she holds the Charles Desor Chair of Engineering. Claire obtained her PhD degree at Berkeley. She then joined the faculty at Stanford for almost 10 years before returning to Berkeley in 2005. And Claire has made remarkable contribution in a number of areas, including hybrid system control and decentralized optimization with applications spanning from transportation to system biology. And more recently, she's been working in the exciting area of safe learning and made remarkable contribution by integrating machine learning and control theoretic methods. And her work has been recognized by many different awards, including the Donald Ekman Award from the American Automatic Control Council and the IEEE Transportation Technology Award. And today, Claire will talk about how to model the interaction between different agents for the design of autonomous system. So with that, the floor is yours, Claire, and thank you so much for agreeing to be our speaker today.
Oh, thank you. Thank you for the invitation, Francesca and the organizers. It's a pleasure to give a seminar here in this seminar series. I'm going to talk, the title is a little broad, but I called it Modeling Other Agents. Within my group, this is something that we've been thinking about a lot in the context of autonomous systems and safety, and how we represent other agents in the environment around an autonomous system. And I kind of emphasize safety here. So we would like to ensure that the designs that we make and deploy on autonomous systems result in those systems being safe in real world environments where there are other agents, and you know, both the perception and the modeling, the perception of the environment and the modeling of other agents is important. Now I'm going to, oh, okay, good. So I've got the chat here, and if you have any questions, feel free to either chat them, as Francesca says, or unmute yourself and just ask. Okay, and it's from an engineering standpoint, my background is in control engineering. These kind of traditional notions of safety, when we think about engineering systems, we've designed systems so that the autonomous component or the automated component is typically not having to deal with many other agents. So for example, autopilots in commercial aircraft, they're, you know, typically honing in on the own aircraft, the control of the ego vehicle, not considering other vehicles. And of course, you know, an air traffic control system is a safety critical system, but that component of dealing with other agents is done right now manually by controllers on the ground. The rail network, it's a similar, like even the design of the system, the way in the air control system flight routes are designed, or you know, the rail system, they're designed in such a way that interaction with other agents is minimized. And even in our robotic systems, you know, robots, for example, manufacturing robots are in cages, right? So they can, you know, they can perform their task while minimizing the interaction with other agents, like the operators who are sitting outside the cage. But multi-agent interactions are everywhere, and as we think about the design of autonomous systems today, whether it be on the ground or in the air, we're faced with thinking about how we model and, you know, infer the actions of other agents. So this is actually an old slide or an old animation of real data from the air traffic control system. Sector 33 is a sector of airspace in the Oakland Center. Aircraft, these are air routes coming in from the East Coast, coming into San Francisco, or in general, the Bay Area airports. And it's a particularly hard sector for air traffic controllers to control. Because there's many of these kind of merging points of routes as they come into the main trunks coming into the Bay Area. And we also have this north-south route that aircraft are going through. So this is high altitude traffic, and just being able to think about automating some of what air traffic controllers now do manually would require this both awareness and prediction or understanding of what other aircraft are going to do. So this is just a result of one of our, so this is actual real aircraft data being played back, and the result of one of our control algorithms for understanding when and how to automatically deviate aircraft to following kind of the rules of air traffic control, so that a conflict or a loss of separation is avoided. And so that's today's system, thinking about automating today's system, but there's even in the airspace, there's a growing number of new applications. These are just some images of both drone applications. Amazon and Google are kind of the big firsts here, but emerging companies like this amazing company Zipline. It's a Bay Area based company, but it started its operations in Africa, doing automated delivery of medicines to remote areas. And now it's come back to the US and is partnering up with Walmart, for example, for medical delivery systems. Down on the right, bottom right, is Lilium. This is one of a growing number of air taxis that are being designed. Lilium is a German company. And you can see there's these interesting rotors. That's actually a tilt rotor system to enable it to do a very short takeoff and then go into a conventional flight mode. So, new growing markets for air travel that are not the traditional large aircraft open up, even more the necessity to try to understand in either an automated or a semi-automated way how to think about safe multi-agent interaction. And, just sort of thinking about bringing the kind of legacy system that we just talked about in the bottom left, how do we take the current architecture, a sort of rigid architecture of flight routes as well as sectors of airspace, and as we design new architectures for our infrastructure systems like air transportation, like road transportation, how do we think about maintaining safety primarily, but also this kind of simplicity, so that even if a system is automated, there's an ability for humans in the loop to understand the solutions and to be able to intuit the behaviors. And then third key is the ability in any automated system to be able to adapt to new information. And that's really what we're talking about here. It's either kind of perception of the environment, but in particular, perception and understanding and inference of other agents' behaviors. So we've been doing quite a bit of work on these kinds of systems over the years. For example, with NASA, we've been working, and we're currently working on a project with them to design automated collision avoidance systems. We've also worked on a project with them to design forced landing systems. If there is an issue, how do you, for a drone system, for example, how do you design a safe forced landing system? Okay, so in this talk, I've planned to talk about three components of our research, or three kind of areas that we've been working on. The first is a project, or a set of projects that we've been working on in my group for quite a long time. It actually started when I was a PhD student. And that's the idea of reachability and a game theoretic method for computing reachable sets for multiple agent interaction. So we're going to start there as kind of a launching point and talk about the game, how we encode interactions between agents, and what the value of the game means, and the kind of computational results that we've developed. Then we're going to move into talking about two more quite recent projects. In fact, these second two projects are active projects within my group and you know, current research that we're doing. The first is a computationally efficient method for many agents, which tries to relax the worst case, we'll talk a little bit about this first case, but the kind of min-max or worst case assumptions that we've been using in reachability computations. And then the third, I'd like to continue that theme and talk about, in that kind of context of a computationally efficient method for many agents, how might we think about, and that method relies on these so-called rationality parameters of other agents. How might we think about learning those automatically? So incorporating learning into these game theoretic schemes. Okay, so let's launch into the first component. And as I said, this is, let's see if I can move this. I think can you see this, you are screen sharing bar here? Maybe not. Usually, I can't remember if it shows up on Zoom, but I'm going to move it so that it's not blocking the references. But as I said, this is work that we've been working on for a long time. In fact, it started when I was a PhD student, and this is started as a collaboration with John Ligeros, who's a longtime collaborator and friend in this work, when we were working on game theoretic methods for safety specifications for hybrid systems. And that was really the beginning. We then, in my research group, when I was kind of launching this as an assistant professor, started focusing more on the computation of these reachable sets. So I'm going to talk a little bit about this today because it's relevant for the ensuing parts. And then I've also given a reference down there at the bottom to a recent tutorial that recent a few years ago, but recent in the scheme of the other papers. Tutorial that we've written about Hamilton-Jacobi reachability, and I think it's a good, it's kind of a good overview, and it talks about, you know, the framework, the actual, you know, equation that we're solving and its derivation, as well as the computational tools and a number of examples. Okay, so what is Hamilton-Jacobi reachability? So I'm presenting it here in terms of a dynamic system where the state is Z, so this is a continuous time, continuous state differential equation, and it's got a state Z that is you know, an n-dimensional state, control input and disturbance input. So it's a dynamic system where the control, the designer has the freedom to choose the control input to within bounds. Yet there's, we incorporate in the model disturbances which can act on the system, and we don't know what those disturbances are. They may be in the air traffic control system, for example. If we're thinking about collision avoidance with other aircraft, those disturbances, we typically represent the actions of the other aircraft in the system. But, you know, this is a general dynamic system. If we're modeling a single aircraft autopilot, for example, those disturbances could be wind or weather acting on the aircraft. But in this multi-agent scenario that we're interested in particular for this talk, I think it's useful to think about the control and the disturbances, the control and the disturbance as two players. And as you have more disturbances or, you know, more actions, you increase the number of players. So there are two players in the two-player case where they're acting against each other. And this is the perspective that we've been taking for a safety critical system. So a reachable set then is the set of all states for which, for all possible controls, there's a disturbance which can drive the system state into an unsafe region. We'll call that an avoid set over a given time horizon. And because it's got this, for all possible controls, there exists a disturbance, we've been using a game theoretic, a zero-sum game theoretic framework to represent that reachability problem. So reachability is posed as a game where the disturbance is attempting to force the system into an unsafe region, into that avoid set, while the control is attempting to keep the system safe. So it's this this worst case perspective is important here, and it's not that we will always apply like the control which counters the worst case disturbance. We hardly ever do that. And so the reachability framework is used to compute a region for which you can guarantee safety. And then within that region, as long as you're not on the boundary of becoming unsafe, you can do whatever you want. You can optimize, design a control to optimize for some other criterion, for example. But this kind of reachability worst case is really to try to separate the state space into those states that you can guarantee, for which you can use the control to guarantee safety, and those for which you cannot use the control to guarantee safety. And I see there's a chat message. How restrictive is the zero-sum assumption on the definition of reachability? Yeah, that's a good question, and that's really what I'm talking about here, is that it's a formulation that allows us to compute boundaries of sets. And in that sense, it's not restrictive because we only use the worst case control when we are on the boundary of becoming unsafe. And that'll become a little clearer as I show the development of this. Another question is, what is the functional form of F? Yeah, that's a good question too. This is a vector field, and it's a function which is Lipschitz continuous in the state and assumed to be piecewise continuous in the control and disturbance. So the state is a state value, but it's also, this is actually a trajectory. So these Z, U, and D are functions of time themselves. And then F is a function Lipschitz continuous in the state variable and piecewise continuous in the control and disturbance input. Okay, so let's explain this a little bit more through the development and an example. So this is just a pictorial representation of what I'm describing here. And I'd like to thank Sylvia. Sylvia's a previous PhD student. She just graduated from my group, and now she's an assistant professor at UCSD. Okay, so in this is a two-dimensional depiction where Z has n is equal to 2, so two-dimensional state. The avoid set is just this disk around the origin, and so the idea of computing a reachable set over a particular time horizon is to compute these states. So everything within, this is an example for a particular choice of F. Everything within this black region represents those states for which, for all possible control inputs, there's a disturbance which, under the dynamics of the system, could drive the system to this avoid set over that time horizon. Somewhere within that time horizon, initial states that start in this region can get into the avoid set. Okay, so how do we compute that reachable set? This is just kind of a picture of the solution. How do we get there? So we represent, the idea here is that we represent sets as sub-zero level sets of functions. So this value, this value of the game is, in this case, this representation of the avoid set. The set, like our goal here is to ensure that we don't get into or for the control to ensure that we don't get into this avoid set. So we're going to encode that avoid set as the value of the game. So we define some function L of Z over the state space such that the sub-zero level sets of L represent those states inside this avoid set. And I'm using this script L to represent the avoid set. Okay, so this is just one possible example of like a signed distance function, which could be the function L, which we need here. So inside the set, L is negative, and outside the set, L is positive. So this is the cost function. And then the value function is really where we start to encode this information pattern of the game or the actions of the other agent. In this case, we have, we're kind of assuming that the ego agent is ourselves, the control, and the other agent is disturbance. So here the value function over the time horizon, so it's a function of state and time, is is representative of this minimum cost of trajectories of the system starting from state Z and evolving over this time horizon T, right? So this value is encoding future penalties or rewards incurred by the system if you start at state Z at a particular time over that time horizon. Okay, so we encode that. This is kind of a pictorial representation, but we take that function L and we evaluate L over trajectories which start at state Z and evolve over the time horizon T. So it's the minimum over that time horizon of the function L evaluated on a trajectory of the system. Okay, but here, how does the control and disturbance come in? We can actually, use the control to our advantage. And remember, we don't know what the disturbance, which could represent the actions of other vehicles, we don't know what it's going to do. So we're going to assume that it could be doing its worst to get the system into that unsafe region. And so, this value function then, like a choice of value function, which makes sense then for the information pattern of the game, is to define the value as the minimum cost of the optimal trajectory of the system starting from state Z over time T. And the optimal means that the control is trying to maximize this function L, while we don't know what the disturbance is going to do. So we're going to try to, as the control, maximize the value of L while assuming that the disturbance could be trying to do its worst, which is to make that function L as small as possible, right? So the action of the disturbance is trying to get you inside this region where L is negative, whereas the control is trying to keep you outside that region where L is positive. So with that value, then we can set up the game. We can define the update equation, which in this case is a Hamilton-Jacobi-Isaacs, the game. So Hamilton-Jacobi-Isaacs PDE. And this Legendre transformation, which is always really nice, right? You go from this functional optimization to this kind of static optimization over actions in D, as opposed to trajectories, like control input trajectories over this time horizon. So the H function, that's what we call the Hamiltonian. It's a function of the state and the gradient of the value function. It's the max over U, min over D of the inner product between the dynamics and the gradient of the value function. Now, this is, so we can derive this, and we have derived it. In fact, that derivation is kind of in these two first papers that I've referenced here, where the second paper really presents that derivation with an eye towards computing it numerically. But just the intuition, there's kind of a lot of nice intuition in this Hamilton-Jacobi-Isaacs PDE. If we look at this right-hand side, this is an inner product between the dynamics at any point Z with acting on a control with a particular disturbance, and then the gradient of V. And if we think about, this function V, just at our initial condition here, where it's representing simply that avoid set, the gradient at any point represents an outward pointing normal. So just an outward pointing normal to that set. So what we're doing is we're looking at a particular state Z. Let's just take a state here where my arrow is on the boundary of that, or on the surface of this function here. Let's go down here and look on the boundary of the zero level set. A state Z, where we look at the vector field representing the dynamics. What's the next value of Z given the best control over the worst disturbance? So given that the control is doing its best to maximize this inner product, and the disturbance could be doing its worst to minimize that inner product. And if we think about what that inner product means, it's basically that, in this three-dimensional system, it's just a dot product between the dynamics and that outward pointing normal. So maximizing that dot product means that it's trying to push the dynamics outward. It's trying to, minimize the angle between F and that outward pointing normal. thinking that the disturbance could be doing its best to minimize that inner product, which means make that angle between those vectors as kind of obtuse as possible. And we can show that that update equation can be represented. So basically that PDE with the initial data given by that function L can be represented as, that Hamilton-Jacobi-Isaacs PDE can be represented in this form. This is called a variational inequality form of that PDE. So it captures both the PDE, which you see here. Here I'm using H, the Hamiltonian, to represent that max min of the inner product, and the initial data L. And that's the initial, I've lost my pointer here. Where is it? There it is. The initial data L minus V of ZT. Okay, so this is an interesting representation of that PDE. But by solving this PDE, it says that the minimum of the PDE and the initial data must always be equal to 0. So let's think about that for a second. So, the PD, if we set this function here equal to 0, that's the Hamilton-Jacobi-Isaacs PDE. But we're also including this initial data. This captures both the value of the data at time capital T, so the kind of initial set that we're starting with, this avoid set, but it also, it's a function of T as well. So it ensures that over time, we're capturing all states that could enter that from some state Z over the time horizon 0 to T, all states from which there's a trajectory that could enter that avoid set and then leave it again over, still over that same time horizon. And that state would be marked as unsafe in this case because it entered even though it left at some future time in the time horizon. So once a state has entered that unsafe set, we want to record the initial state that that state emanated from as unsafe. And that's what that variational inequality does. Would this notion of reachability have any link to Blackwell reachability that we use for finding correlated equilibrium in economic game theory? That's a good question, Ayan. I don't know. That would be really interesting to take a look at. I know a little bit about the idea of correlated equilibria, but the concept of Blackwell reachability, interesting. I don't know. It would be interesting to take a look at that. So now let's just continue with this. Yeah, okay, so what are we doing here? We're just, and this is again an animation thanks to Sylvia, we're computing, but basically we're solving that update equation given the initial data. And so what we've done here is we've taken that initial set and starting at that initial set, we've computed over the whole state space the solution to that Hamilton-Jacobi-Isaacs PDE. And at each stage, we've captured, so I mean, at each stage, meaning at each point in time, we've captured the 0 level set. And so at time T, after we've computed that backwards reachable set over that time horizon, we can capture and represent that set that I showed you earlier. So we're representing sets as 0 level sets of functions, and then we're solving this Hamilton-Jacobi-Isaacs PDE to update that function over time, always capturing its 0 level set to represent the reachable set. We can also do this computation in the presence of constraints. So here in this animation, we've got our original avoid set, or the set that we want to avoid, but we've also got, for example, other sets that we might want to avoid representing constraints in the problem. So this can be incorporated just by taking those constraints. So we've got, our L, which is our avoid set, another set of constraints that we want to avoid. We can incorporate those into the value function, also into the PDE, and then basically do that same computation. And with the computational toolbox, which I'll talk about in a second, is basically computing these sets by computing these functions. So representing the constraints as functions, it becomes an intuitive and actually a computationally straightforward way to include these constraints in a set propagation. So here, that presence of that obstacle also can be, incorporated, so that now this backwards reachable set is kind of qualified by the presence of that obstacle, and that we use this term reach avoid set. So the set of states which reach the green region while avoiding the red region. Okay, so just showing a kind of concrete example, which may go back to this multi-agent interaction. So these are two agents, two aircraft. This is a game which is called the Game of Two Identical Vehicles. It's an old game, kind of posed and presented and solved via trajectory propagation back in the 1950s by Isaacs, hence the Isaacs of the Hamilton-Jacobi-Isaacs equation. But it's two vehicles. I've shown them as aircraft, a control and a disturbance aircraft. The goal is to keep the disturbance aircraft outside of a 5-mile radius in the plane from the control aircraft. And here, both aircraft have a constant velocity. They're flying at a constant velocity. Their control actions represent their angular velocity actions. So there's a control action, which is the angular velocity of the blue aircraft, and a disturbance action, which is the angular velocity of the disturbance aircraft. We don't know what that disturbance action is, but we're assuming that both the control and the disturbance actions are bounded to within limits. So the velocities are bounded. The state space is the XY position relative. It's two aircraft, that's nice. So you can represent the state as a relative state between the two aircraft. So it's the XY relative position and relative heading between the two aircraft. And so Ian Mitchell, who's a former PhD student and who's now a professor in computer science at the University of British Columbia, this was one of the first examples that he computed when he was developing a toolkit, a computational toolkit to solve these reachability problems. And so you can see here just some of, in this example, the Hamiltonian. So here you see this max over the control set, min over the disturbance set of the inner product between a costate P and the dynamics. So at this costate is the gradient of the value function. These are the relative three-dimensional dynamics. Here we're using A for the control input and B for the disturbance input. And then we've just assumed these simple bounds from -1 to +1 in a sort of dimensionless representation of the angular velocity. So x1, x2 represent the positions, and then the relative heading is x3 in this case. And this is the solution. So we'll talk in a second about the computation, but this is the basically solving that reachable set over, in this case, it's over an infinite time horizon. It actually closes off. That set stops growing at a particular time for these values that I've shown. And the set represents exactly what we're trying to compute. The set of all states for which, for all possible control inputs, there's a disturbance action of the red aircraft, which could cause that red aircraft to get inside this 5 nautical mile disk. You see that disk in 3 dimensions is represented as a cylinder because the 5 nautical mile disk, it doesn't matter what relative heading you're at, you're still unsafe if you're within 5 miles of each other. And this set is interesting. It kind of curls around. It's the dynamics allow it to kind of curl around that cylinder as it grows. The most unsafe configuration is the value when the relative heading is such that the two aircraft are pointed directly at each other. So that's the direction of maximum growth, which we would expect. That's the most unsafe condition here. Okay, so this is computed by solving that Hamilton-Jacobi-Isaacs PDE. And just to give you a little more intuition, this is another, this is kind of a simulation, but using that reachable set. So I've got kind of 2 snapshots here. This is that reachable set that we computed on the previous slide. And then we've kind of operationalized it by taking two scenarios. One in which the control aircraft is, the disturbance aircraft is outside of the reachable set. So it starts out with an initial configuration outside, which means that there always exists a control input such that the control aircraft can maintain that 5 nautical mile separation. And a second instance where the disturbance aircraft is actually inside that region. And these are two-dimensional slices shown for the given relative heading that you see here. So they kind of, you can see they represent that, almost that pi condition where the two aircraft are pointing towards each other. So it's kind of a slice around here of that three-dimensional set. And here's where we come back to that question earlier about like the conservativeness of this solution. So the way the simulation runs out is or rolls out is that the control aircraft is basically trying to fly over here to the right of the screen in both cases. And that's what it's trying to do. It only deviates from its control action when the disturbance aircraft comes on the boundary of the reachable set, and then it applies that max over U. So that computed control that comes out of the Hamilton-Jacobi computation, which guarantees that the disturbance aircraft will stay outside of the set by applying that control when the disturbance aircraft is on the boundary of the set. Okay, so let's just take a look at that. So here's state space, unsafe states. Okay, so there you see the control aircraft deviating from its desired profile, which is to go right, just because it knows it has to apply the best case control action to keep the aircraft outside, to keep the disturbance aircraft outside of that reachable set, because once that disturbance aircraft is inside the reachable set, there's no guarantee that it could stay safe. There is a disturbance action which could cause collision. And here you see that in this instance, here the disturbance aircraft starts inside, and despite, you know, the best possible control action, they lose separation at this point. Okay, the disturbance aircraft could have done something that wasn't optimal, and the control aircraft could have, you know, applied its best control action and gotten that red aircraft outside of the set. But in this case, the disturbance action played an action which caused the two vehicles to separation. So it's conservative in the computation of the set and the and this kind of least restrictive control law to apply on the boundary of safety. But as long as the configuration of the state, as long as the state is outside that reachable set, the system can do whatever it wants. You can optimize for some other criterion, like here, a performance criterion to fly to the right. Okay, so Ian Mitchell was the first in the group to really develop this computational framework. He has a code repository for this level set. We call it level set methods because it really is. It's computing the solutions to this Hamilton-Jacobi-Isaacs equation using the idea of propagating a function and recording the zero level set of that function. Okay, so there's some links to that. And then in more recent years, so this is Sylvia and Mo. Mo is also just graduated a few years ago. He's a professor at, he's also a professor in Vancouver. He's a professor at Simon Fraser University in Vancouver. And there's Sylvia, who's just started at UCSD. We've been developing in our group a number of wrappers for this reachability toolbox. Functions which make it easier to use. And there's the code, a link to the code repository for that. So this helper OC provides a kind of user interface that links directly to the level set toolkit. Okay, here's an example that we did early on. These are 4 quad rotors. And there's, if you look on the right here, here's 4 students. They're joysticking the quad rotors around. But when the quad rotors come within the reachable set, this is a snapshot of the data. So when one aircraft comes within the reachable set, it's reachable set with respect to another aircraft. So it's possible collision zone. The autopilot on board the aircraft takes over and guides that vehicle away from the reachable set. and that is done for a certain period of time, and then control is given back to the students. So it's a nice example of a 4-vehicle scenario where we were able to solve this. So this is a 3 dimensions per vehicle. 4 vehicles, that would be a 12-dimensional problem. That's a computationally challenging problem for a PDE solver. But this scenario is one that you can decouple. So you can take that 4-vehicle scenario and divide it into pairwise. So these different pairwise problems that can be solved in a distributed way. And that's not always the case, but it's the case for this scenario. One of the big projects that we've been working on with Samuel Bansal, another PhD student who just graduated, and now he's an assistant professor at USC, is to develop a computational toolbox that's a grid-free method. So unlike our level set toolbox, which Ian developed, the idea here is to try to go away from a grid, so you can get away from these exponential complexity of solving this what's essentially the Bellman backup equation over a high dimensional grid. And so we've been exploring the use of a neural network to learn a parameterized approximation of the value function, and then use the equation that we know has to be solved, this Hamilton-Jacobi-Isaacs PDE, for fitting the parameters. So the idea here is you want to represent the value function as a neural network and learn a parameterized approximation of this value function. But typically the parameters, so this V of theta is the neural network representation of the value function V. They're obtained by supervised learning, where a value function is assumed to be known at some states. But even obtaining these values is hard. So, and it's especially hard in high dimensions. So the idea behind this gridless computation was to develop a self-supervised learning method where we use the PDE itself as a source of supervision for the training of the neural network. And we find optimal neural network parameters by minimizing the PDE violation error at randomly sampled points. So the idea is to update the parameters to minimize that violation error, and that means that you no longer need values for samples, and that's been the key to scaling to high dimensions. So this kind of shows in this slide that loop of random samples, compute the loss function. So here's the Hamilton-Jacobi PDE, here's that initial data, fit the value function, and then just repeat. We use a sinusoidal representation network here as the individual neurons. That was really important because we're fitting a continuous function. And although we tried other representations, this one really snapped on to a good solution. So for that 2 aircraft, that game of 2 identical vehicles, where we've, we kind of use it as a litmus test, because in its lowest dimension, it's like a 3-dimensional problem. We can solve it actually analytically, so we can use it as a comparison for both our level set toolbox, the analytic solution as a comparison for both our level set toolbox as well as for this neural network approach, which we call deep reach, for deep neural networks for reachability. And we get a very high quality approximation of the value function. So much so that we're now able to solve problems we've just solved a 16-dimensional state problem using deep reach. This picture here is a 3-vehicle with 3 dimensions each, so a 9-dimensional collision avoidance problem. And it's nice because, so it's 3 vehicles. There's 1 pursuer and 2 evaders. And the pursuer is trying to cause a separation, or cause a loss of separation between any pair. So between itself and either one of these, or indeed between the 2 evaders themselves. And if you decouple the problem, like I showed in my earlier quadrotor problem, then you get a under approximation of the reachable set. That's the blue set here. Whereas deep reach gives you this, this pink region. This is a 9-dimensional state space, and I'm showing this projection onto 2 state dimensions. X8 and X7 are the position coordinates of the pursuer for these, in this slice, these fixed positions of the evaders. So if we just look at 2 points here, 2 points of where this pursuer can be, if it's inside that unsafe set, so that's this simulation in the middle, you can see that the minimum distance between the two evaders and the pursuer drops below the required threshold. Whereas for this gray point here, which is outside of this computed set, you see that separation is maintained. So this deep reach is giving us a numerical approximation of the reachable set, and it's kind of current work to examine this and to think about the hyperparameters of the network and all that. But we're getting really good results in terms of accuracy of representation, where we can compare it with an analytic solution, and it's allowing us to compute solutions in higher dimensions than we've ever been able to compute before. Okay, so I want to now, in the last minutes of the talk, just talk about our current work in relaxing this worst case assumption about the behavior of other agents. So I'm going to talk about a computationally efficient method for many agents. And then if there's time, I think I'll probably just have time to mention what we're doing in learning these rationality parameters of other agents at the end. Okay, so this is a kind of a motivational example, and I decided to present because I knew we'd be only have like about 10 or 15 minutes left when I got to this point. But I decided to represent this this part of the talk more through an example than by presenting the math up front. But the question as we think about relaxing the, okay, so let's just, in this first part of the talk, we've been talking about reachability, and we've kind of qualified what we meant by this worst case perspective. So we're computing a reachable set using a worst case perspective where the value function of the game is solely represents the safety condition, whether you end up in an unsafe condition or whether you don't. So there's not really a running cost. You saw that when we designed the value function. There was only an end cost based on that kind of game of kind. You're inside the set or you're outside the set. The idea of, so it's good for, as we said, delineating the state space into safe regions and unsafe regions, and moreover applying this control to use when you're in danger of becoming unsafe. But how can we think more generally about the actions to apply away from the unsafe region, and how we moreover think about encoding the actions of other agents in those scenarios, rather than just thinking of that the other agents are going to always do their worst case. So we were interested and started to work on problems where we thought about new frameworks for encoding this interaction between agents for multiple agent scenarios in a way that admits efficient computation. And this simulation that I'm showing on this slide, there's two movies here. Let's just show those again. On the left is a merging scenario where the blue car is trying to merge in the lane to the left in front of the yellow car. Let's just go back and play that again. Okay, so this is the kind of desired polite merge where the blue vehicle speeds up a little bit, so to reach the speed of the yellow vehicle. This is the kind of non-polite where you just merge and then you're kind of maintaining the velocity that you've been driving at over in the right lane, and the other vehicle, the yellow vehicle, has to slow down. So this is a motivating scenario because on the right, this is actually to the particular game that we'll talk about. This is the open loop Nash equilibrium solution. So this is what's typically used. It's kind of the state of the art in game theory with state and input constraints, is to use an open loop Nash equilibrium. Perhaps you'll use it in a in kind of an iterative way, like an iterative best response. But in this case, in the open loop Nash equilibrium solution, the blue vehicle, so the yellow vehicle is expecting that the blue vehicle won't react to it, so the yellow vehicle actually slows down. And so that's it's interesting because this is in the automated vehicle community, this is kind of that where a lot of, iterative best response is used. This is kind of like that hesitant behavior that you see in autonomous vehicles. So that blue vehicle is going at a particular speed, it's merging in front of me, I'm assuming it's going to maintain that speed, so I better slow down. Whereas in actual fact, most drivers do this polite merge, right? You speed up to the speed of the traffic in the lane that you're going into. So this work now is with Forrest Lane, who also just graduated. He's an assistant professor at Vanderbilt. And the example that I'm presenting, we presented at ICRA this year, but we have a journal version on this game theoretic framework. And I'll just say now there's an archive link to this where we're studying the idea of a generalized feedback Nash equilibrium. So to try to capture this idea of a polite merge in a feedback game setting. So again, I'm going to try to explain it briefly pictorially rather than go into the math, and then I'll just show you the math in a second. But the idea here is that, and in this overview, here, the blue vehicle in the left lane represents the ego vehicle now. So the idea is that that ego vehicle maintains multiple hypotheses about the intentions of other vehicles. So in this case, for example, it could have a 20% or an understanding that with 20% probability, the red agent will change lanes, and 80% probability it will stay in lanes. Okay, so it's got the probability of changing it. And so it duplicates the red agent, one version for the red agent that stays in the lane and one version for the vehicle that changes lanes. So given that, so that's staying in lane, changing lane. So then the question is, what should the ego vehicle do? Since it may be overly conservative to avoid collision with respect to both trajectories, especially since there exists a relatively low probability of lane change here. And that's really the kind of background of the framework that we've been working on. So our method introduces an interpolating parameter. In this case, in this example, it's an interpolating probability. So P is a parameter which goes between 0 and 1. And P here represents the probability of a lane change. So when P is 1, the ego avoids the hypothesized agent. Okay, so that's here shown on the left. And when P is equal to 0 over on the right, the ego is ignoring the hypothesized agent. And then there's kind of intermediate probabilities which interpolate. So with this kind of understanding, we've been developing a novel optimization formulation with a game theoretic formulation, which leads to the formulation of a generalized feedback Nash equilibrium. So this is an optimization problem in which other agents can be assumed to react to the ego's behavior. So that's what's missing in the open loop game, right? So we want to assume that the other agents are going to react to us. So how should we behave so the other agents react to us? In this example, the non-ego agents are nominally responsible for collision avoidance with the ego vehicle, but by increasing that probability, the interpolating factor from 0 to 1, the responsibility of collision avoidance is transferred from the non-ego to the ego vehicle. Okay, so for every hypothesis about the intentions of other agents, we duplicate that agent and assign collision avoidance responsibility based on the probability of that hypothesis. So you can see here in the ego case, it's including the notion, the objective of the other agents in its value function, and then just optimizing with respect to its individual constraints. And then we have however many versions of the other vehicle as there are hypotheses about its actions. And it has this responsibility for satisfying the constraints. And so you can see where that interpolating probability comes in, that nominally the other vehicles are responsible for collision avoidance, but as you increase P to 1, that responsibility transfers back to the ego vehicle. Okay, so that polite maneuver can be replicated now with this feedback Nash equilibrium solution. Basically that, how should I act so that the other vehicle knows how should I act so that I can get the other vehicles to do what I want them to do? That kind of multiple interaction that you need a feedback game to represent is represented here. And, you know, we can make this more complicated, right? So here's a couple of different scenarios. On the left, we have, you know, a similar scenario, 2 hypotheses regarding the intentions of the red agent now. So blue is always ego here. And that could be stay in lane or change lanes. Okay, so that's similar to what we just saw. But then we could, you know, look at other scenarios. So in this middle scenario, there's 2 hypotheses with respect to the intentions of the red agent, which are, is it going to drive fast or is it going to drive at a normal speed? And then we can start to couple these, right? So different hypotheses about different vehicles. So you can get, you know, this multiple vehicles, multiple hypotheses. And so it's been really important to think about this in the context of a computationally efficient methodology for solving them. We've developed a couple of different frameworks depending on assumptions on the dynamics and the value function. The first is an iterative Lqg, so a linear quadratic game where it's an iterative solution, but it's modified to deal with state and input constraints, which we have here. But in general, we solve these using a sequential quadratic programming like algorithm, which solves for the first order necessary conditions for the game. And then an LQ problem is solved at each iteration using an active set approach. So basically, we're using in that second step an equality constrained linear quadratic regulator problem. So this is a computational framework, which is, though it's not yet real time, we feel like just with some optimization of the code, so we're using MATLAB, et cetera, to turn it into compiled code and to, you know, optimize the way we deal with the active set approach, that we can make this real time for scenarios like this involving multiple agents with multiple hypotheses. Okay, I'm coming to the end of the time, so I think I'm going to leave that last topic, which is, you know, learning the rationality parameters. So, right, rationality parameters, well, specifically in the case that I just talked about, how do we learn that interpolating probability? More generally, when we're looking at models of other agents, like humans walking around in scenarios, and we model those with, you know, different representations, like Boltzmann models, for example. How do we learn the parameters of those models? And that's been work that we've been doing jointly with Anka Dragan at Berkeley, with our joint PhD student, Andrea Baichi. But I'll leave that for maybe a different talk another time and conclude the talk. Let me just go down to the last slide. So yeah, so we talked about reachable sets and the concept of this reachability using this best control against worst disturbance and how that can be used in safety critical scenarios. And then we relaxed that assumption about, you know, computing worst case on the boundary and started to think about how we can encode these kinds of multi-agent interactions as feedback games, and have really been thinking about computationally efficient methods for solving these. And then finally, I'd like to conclude by thanking a number of folks. These are all students or former students. Actually, the folks in bold are current students who've been working on problems like this or related to this. And then for this work, I'm listing several former students who've gone off to different universities to be professors or to different companies in their work in developing this Hamilton-Jacobi framework of reachability and the kind of approach to solving these games. And I'd also like to thank a number of our funding agencies who supported this work. So thank you very much for listening and participating, and I'm happy if there's time just to answer the questions that you have.
Perfect. Thank you so much, Claire. This was an amazing talk. So as Claire said, like if you have any question, you can unmute yourself and ask them directly. Maybe I can start with one question, Claire, that I was thinking about. So actually in the first part of your talk, like this core idea of describing the avoid set with a function, right? So that is the void set is going to be the 0 sublevel set. I was wondering, like, there's multiple functions that you can choose for doing that. So is there some like particular techniques of how you choose, or is there even a way to define what's the best function you can use?
That's a good question. I don't know how to define the best function that you can use, but even for that problem we spoke about, there's a sign distance function, which is the one I just showed there, but you could use a different metric for a distance, right? So then that could become a curved function, or you could use a minimum time, which is not necessarily the same as a minimum distance solution. And so it kind of depends on the problem at hand. So whether you're looking for minimum distance or minimum time, but also, the numerical solutions are such that regardless of which function we choose, we typically need to, there's kind of a regularization step that we apply in the computation, in the level set toolbox, so that at the boundary, the value function, as you propagate it, it kind of maintains a nice value. The gradient doesn't get really steep or too shallow. So we're often, computing for a little bit, regularizing around the boundary, computing and continuing. And then, we've had good experiences with sign distance functions, as well as like a Euclidean distance function. But it's a good question. What are the properties of that initial function L, so that you can maybe minimize the number of regularizations that you need to do? It's something that we have more of a like empirical experience than we do an analytic experience there.
Perfect. Is there any question from the audience? Oh, I see one in the chat, maybe.
Yeah, are there any system dimension limits to implementing the Hamilton-Jacobi method? Urson, that's a great question, and it's something we've been focusing on for a long time. If you're going to do straight Hamilton-Jacobi using the level set methods, depending on the dynamics and depending on the grid size, because it's basically the number of grid points, right, which is exponential in the dimension of the continuous state. So if you have a coarse grid, you can go for higher state dimensions, but it's typically around 6 or 7 continuous state dimensions for straight Hamilton-Jacobi, no decomposition logic or anything. We've done a lot of decomposition work. In fact, Sylvia Herbert, who I talked about her work, her PhD work was looking at how you take high dimensional or higher dimensional differential equations and decompose them into subsets where you do the computation in the subsets in parallel, and then piece together an over approximation of the reachable set, or an under approximation, depending on what you're trying to solve. And in those, we've gotten up to, it depends on the problem, but we've solved in the decomposition problem of 16 dimensions. With deep reach, we've also just solved a 16-dimensional problem directly. But the question, we don't have a good comparison. I mean, we have our decomposition comparison, but it actually looks like deep reach is doing much better than the decomposition. So as we get into higher dimensions, I think the use of, this is where neural nets is really useful, right? For solving these, for implementing grid-free computations of some of these scientific computation problems that have been around for a long time that people haven't been able to solve. We're seeing papers pop. I mean, we worked on the Hamilton-Jacobi, but there's a cool paper from Caltech about Navier-Stokes, solving some of these problems to a level of detail that haven't been done before, just because the neural net allows just a lot of optimization on where, like what grid points you actually choose to do your computation at. So dimension limits, I'd say we personally in our group have solved 16-dimensional problems with either deep reach or decomposition. And now we're working on a walking robot example with Professor Kaushal Srinath at Berkeley, where it's a order 60 dimensional model of a bipedal walker. We don't know, we're not there yet, but I think that's a really good question, and it's something that we're working on.
Perfect. And maybe I can ask you another question, Claire. So I was curious, like in this first framework that you described, I suppose that you need to know the other vehicle, what its dynamics are. You need to have an idea of like the model of the other vehicle, right?
You
I was
do.
like back at the example that you have at the beginning, that there's many like companies that are developing different vehicles. I suppose each one of these will have some slightly different models, different dynamics. So I was thinking, can you use something like the second part of your talk where you say, well, at the beginning, I don't know the other vehicle that's approaching, what type it is. So I give you like different probabilities of what model this vehicle could have. And then kind of you learn through like while it's approaching or how it's moving, like you kind of tune in the model. So you're kind of safe at the beginning with respect to uncertainty of the model of dynamics of the adversary. And then maybe you get some data and you kind of tune in into exactly what vehicle is approaching.
I think so. I haven't thought so much about that application with the second methodology that we've developed. But what we have done, and you alluded to it in the introduction, is we've done a lot of work in safe learning. So if you have a model, but there's, you can always use not always, but I think in many engineering systems, there's always a rough model that we have of a system that we're trying to represent. So if it's a vehicle, I mean, could be modeled very simply with a point mass moving, right? And then as we observe it, we can gather more information to be able to perhaps fit a better vector field model for that system. And how might we construct the safety certificate, like the Hamilton-Jacobi formulation, so that it's conservative, and then as you learn more about the vehicle, it becomes less conservative. That's typically the direction that you'd like to go in, and those are the examples that we've looked at with safe learning. So I think there are a number of things to be done, including what you said, which is to think about that multi-agent framework with parameters that you want to learn as being a way to represent unknown vehicles or unknown interactions between those vehicles. Yeah.
Perfect. I think like we can conclude. There is one other question in the chat, so maybe we can address that.
Oh, this is a question from Babak about mean field. Do you think it is appropriate to model the multiple pursuit agents as one mean field model? Yeah, I think it is appropriate. And this is it's a really interesting question and a really interesting area, the mean field approach to games. Several years ago, so there'd been some work that we were following from some French researchers. And we tried an initial foray into mean field approach for kind of a multi-agent scenario with lots of agents with very simple interactions. So what I don't know, because it's been a while and I haven't followed the state of what's been going on in mean field games. There's challenges computationally there too, but it seemed like a framework that was really appropriate for when you had lots of agents with kind of simple interaction rules. How it would work for like maybe fewer numbers of agents with more complex rules of engagement is something that I think is really interesting. That it's interesting. There was a new PhD student at Berkeley who's kind of came and started talking about this recently. So we started to kind of look back and see what's been done more recently. But I think that's an interesting question, and I would say yes. I think it's a cool thing to take a look at.
Perfect. Okay, so if there's no other pressing question from the audience, I think we can thank Claire for this amazing talk, and thanks the audience as well for attending. So thank you so much.
Very much. Thanks, Francesca, for hosting. It's a pleasure to see you and to give this talk.
Perfect. Have a nice day. Bye.
Yeah, you too. Bye, everyone.